So, okay, so welcome to lecture number 5 on convex analysis. So this lecture is a continuation of the theme of convex functions. And the last lecture we had these two important notions of lower semi-continuous function and convex function. And most importantly, probably these both properties are characterized by the respective properties of the corresponding epigraphs. So function is convex, and we come to that today actually only if the epigraph is a convex set and the function is lower semi-continuous, if and only if the epigraph is a closed set. Okay, so these are the important things from last time, one thing one should always keep in mind when working with convex functions is that the function value of plus infinity is nothing bad. It's actually, we added this on purpose because if you have the function value infinity, it just means that something is just something you should never plug in into the function. But it's much more handy to deal with functions which which may take the function value infinity. For example, you can just add two functions together which only have real values and the value infinity. If you just add them together, no matter what their domain is, so the domain where they are non-infinite, you still may add them and just in the domain shrinks. It just simplifies the notation. The value minus infinity is much less clear, at least to me, why we should add it. I think, yeah, in some contexts it may be helpful. In our context, we probably just rather not have the function value minus infinity. I don't know of the clear purpose why one would want that, but probably there is one. And some warm-up questions which actually deal also kind of more prepare to the lecture tomorrow, because tomorrow's lecture will be dealing with minimizers of convex functions. But anyway, I asked the questions here anyway, because so convex analysis, as I told sometimes before, one of the main reasons I study convex analysis is to solve convex optimization problems, to find minimizers or minimal values, minimizers to or minimal values of convex functions. So, and then the first question is, if I want to find them, is there some? Does these things actually exist? Okay, so the first question is, if you have a convex function, f is just convex, nothing else, and on Rd, does there exist a minimizer of f? So, meaning that, is there a point x star in the domain of f such that f of x star equals is actually the smallest possible function value? And if I wrote infimum here just to be on the safe side. So if you would know it exists, I could write minimum, but okay, you know this distinction. Okay, so if you have the mental picture that the convex function always looked like this, then it's pretty clear, well, yes, here that should be a minimum. But that's just one picture of convex function. First, it's only one-dimensional, so but many interesting things already happen in one-dimensional. And so, yeah, one thing is convex functions need to look like this. We talked about affine functions are also convex. So in this, if this is also a convex function, then it's pretty clear that it just may even be unbounded from below. So it may just go way down, so that the answer is obviously no. Once you've realized that this is also still convex, because the infimum may not even exist. So, but we agree in this case the infimum may be minus infinite. We agree to be able to calculate with the infinity. So okay, the infimum of this function would be minus infinity. Yeah, but where's the point where f assumes minus infinity? There is none. So an affine function is finite everywhere, because we did not extend the domain. So we did not allow minus infinity or plus infinity to be in the domain of the convex function. One reason is we are working with functions from Rd to R, so and there are many different points which lie in the there's many different possibilities to deal with points in the infinite of Rd. You probably know of the projective plane, the one-point compactification, or whatnot. So there's just no first there's no mathematically simple way or the unique way to deal with infinite in the domain. And the other hand, the other point is from a practical point of view, if the function value lies at some point in the infinite on a real line at minus infinity, then how should we approach this algorithmically? How should we make use of this in practice if f is a real function and you want to have a value as small as possible? Okay, so here the answer is no, because it may even unbound it from below. So and if you have the mental picture which looks like this, that's not totally accurate. This is also something which can be convex, for example. Another point is where existence of minimizers can break down is that functions need not be lower semi-continuous. You know, existence of minimizers in continuity, you probably know the Weierstrass theorem. If a function is continuous on a compact domain, it has a minimizer. So a real-valued function, on a continuous real-valued function on a compact domain always has minimizers. And you need continuity to prove that. Okay, so without continuity, of course, it's pretty clear. You can just have a function which goes like this, and the minimum may be here, but then you just do not let it assume this point, and then let it jump to somewhere else. Let it jump up. But for convexity, we have a few restrictions. So, for example, having it jump up like this here, this does not work. Even if you put the function value here, because this will not be a convex function. If you draw the line from here to there, it is not totally above the graph. So this is not a continuous function, not a convex function. It's also not lower semi-continuous, but it's also not convex. So, but we still may allow ourselves to have the function jump up to plus infinity. So the function I'm now talking about is the function, the graph is like this. At this point, the function value is already plus infinity, and from that point on, it stays plus infinity always. So this is still a convex function, but does not assume its minimum, so its infimum. So the infimum is clearly, so this here, this would be the infimum of f. But there's no point where this is assumed, but we can get arbitrarily close in a finite, so with finite things we plug into f. So the situation for this function is different from that function. This function is practically, we have a problem because if we want to make f as small as possible, our argument has to blow up in some sense. So if the arguments are like parameters, we can tune in for some device such that the output behaves like we want, and we kind of classify the output by some convex function. Then this situation would mean, well, we need to kind of pump up the parameters to some extreme, which maybe we cannot ever realize. Here it's a little bit different. Here's kind of the parameters maybe on the edge. And so an edge is sometimes also a complicated thing. So this is a little bit more practical because we can get close to the infimum with kind of a good parameter. So this here, if a value like that, or if something in x like that, which we could plug into f, this would still be fine because its value is pretty close to the infimum, and it's maybe still realizable, even though we may never be able to reach the exact infimum. So this situation is better than that, but it's still not satisfying, because if you want to approximate the infimum, we may still run into a region where our parameters maybe not be that feasible anymore in a practical sense. Okay, so, but these are two problems. Bounded, unbounded from below may still happen for convexity, and on the other hand, a function may still jump up to plus infinity. And in a non-lower semi-continuous way, which then just kind of blows away this minimum here. But if we kind of forbid these two these two situations, so if we kind of shut them down by some means, so for example, we assume f is now convex, bounded from below, this cannot happen anymore, and also lower semi-continuous, this cannot happen anymore. Does then there exists a minimizer of f? So if we shut down these two pathologies here of convex functions, is this enough? Yeah, and the answer is still no. The answer is still no. And yeah, and the example is pretty simple. You just take the exponential function. So f is equal to f. F is equal to the exponential function. That's nicely convex. It's bounded from below by 0. All values are non-negative. It's even continuous, so it's also lower semi-continuous, and the infimum of f is of course at 0, but there's no point where 0 is assumed. So it's still not enough. We need something else, and we come to that in the next lecture. Okay, but still, one good thing about convexity. So now it sounds like, well, why should we deal with convexity anyway? So it does not guarantee existence of minimizers, and even if we put more assumptions, it still sounds like, well, is it still good or not? Yeah, the main good thing about convexity, or there are many good things about convexity, and we come to a few of them. One good thing is that if you find a local minimum, it's already global. That's one thing. If you have a point which is locally minimal, then it's already globally minimal. Yeah, the reason for this will become clear later. It's by pictures is obvious, but the great thing is that local minimality can be checked by methods of analysis alone, local methods. So directional derivatives at a point, if they are all zero, then we have a local minimum. So we only need to be we only need information in a local region of the function to guarantee its global optimality. So that's one thing which is outstanding about convexity. Another thing is that if you will go downhill, you always go somehow towards the global minimum or the set of global minima. And so there are other things which make it really, really nice to work with convex functions. Okay, so these are the warm-up questions, and it's pretty normal that you get get this wrong at first guess, because convexity sounds so nice, and lower convexity is also very nice. And if you have bounded from below, what else could be missing? There's something missing, but we can only explain that next lecture tomorrow. So for today, we go with chapter 5. It's called Characterizations of convex functions. Characterization of. So we have one characterization of convex sets. We have one definition, and yeah, I just keep on drawing this picture because I like it. One definition of convex set is if we have 2 points, then the line between these 2 points is totally in the set. And the other characterization is then if you have a point outside the set, we can find a separating hyperplane. So characterization from the inside, so definition from the inside, characterization from the outside. So those things are both equivalent. So how about convex functions? Oh, there's also more. And so let's start right away with our first theorem. And the first theorem, 5.1, relates or characterizes convexity in case of differentiability of the function. So if f of Rd to R is differentiable everywhere, then we have the following three things are equivalent. 1, f is convex. 2, the gradient of f as a mapping from Rd to Rd is monotone. And I should probably explain that. Monotone. And monotone means, so now it's a function from Rd to Rd, so the vector of all partial derivatives. But we also assume differentiability, so we assume a little bit more than partial differentiability. So it's a function from Rd to Rd, so domain and image space are the same. And monotonicity means for all x and y in the domain, we have that the inner product of the gradient of f at x minus the gradient of f at y with x minus y, this is always non-negative. This is monotonicity of functions from Rd to Rd. Yeah, so I asked a question in the side in the margin note, why is this called monotonicity? What has this to do with kind of being increasing or decreasing? And the answer comes from in 1D. So in 1D, the inner product boils down to just the product, so this difference times that difference. And if you have a difference of two real numbers, so in Rd these both are real numbers, so these are just real numbers, both this and that. The product of real numbers is non-negative if both have the same sign. So the sign of that is equal to the sign of that. This is what monotone in the case d equals 1 means. In the case in higher dimensions, it's far less obvious what has to do with kind of being increasing, decreasing. Doesn't make any sense because both are not ordered here. But in 1D, monotonicity means that this and this has the same sign. And for example, it means if x is larger than y, then f the derivative of f, or this function here, function value of f has to be larger than the function value of y, which means increasing. And the same if f is smaller than y, x is smaller than y, then this has to be smaller than that. It's the same, it's still increasing. So actually this, what we call monotone here in 1D, it would be increasing. Okay, but there's no, because it's not really about increasing or decreasing here, nothing getting larger or smaller because it's in RD. The name which has been stuck is monotonicity for such maps. Yeah, you can ask yourself, what would a linear map, when is a linear map from RD to RD monotone? It's also not totally obvious, and the answer is also not that, it's not different. Okay, there's a third characterization which we're also going to use is for all x and y in RD, we have that f of y is larger or equal to f of x plus the inner product of the gradient of f of x, times x minus y. Okay, and this is also pretty important. What is here on the right hand side, you probably notice this, this is the Taylor expansion of first order Taylor expansion of f at x. It's a linearization. So this here is the linearization of f. So if we draw a picture with a nice convex function like that, this is our f, and here now that's why this is y, right? This is now f of y. So this is the left hand side of the inequality. And the right hand side is the linearization at some point. This is our point x, and this is our right hand side. Then we have the function which is down here. It's actually this. And now this is one of the magic properties of convexity, that the linearization is always fully below the graph. This is kind of the analog to this characterization from the inside, from the outside. Definition of convexity of convex function means that the secant, so kind of these lines here, are always fully above the graph, and the characterization is they are always fully, the secant is above the graph is below the secant, and the tangent is below the graph, globally. Okay, so this is also one, so local information gives you global information. That's one of the magic things here. Okay, this is the result. Oh no, this is not the full result. There's more. If f is twice differentiable, then f is CVX if and only is the Hessian is positive semi-definite. So the Hessian in every point. Or maybe I should write that more carefully. What I wanted to say is that for all x, it holds that the Hessian of f is positive semi-definite. So this is here, there's some curly greater equal, or maybe I write it a little larger. This is a curly greater equal. So I don't know. This is how I write it, and this means SPD for all x. So symmetric positive semi-definite SPD. And this means that these inner products, these inner products are all non-negative, so for all z. Okay, so in the twice differentiable case, the Hessian alone characterizes convexity. Okay, this is how we can characterize convexity. What about strict convexity? So strict CVX is characterized by strict inequality in 2 and 3. So if you always have strict inequality as soon as x and y are not the same, or if you always have strict inequality as soon as x and y are not the same, then we have actually strict convexity. Here, in the twice differentiable case, it's a little bit more complicated. Hessian of f positive also it's positively finite. Probably I should not use it down in words, but in formula, if it's have it like this. So if the Hessian is positively finite, it's sufficient for strict convexity, but not necessary. So this is the full statement. These three things are equivalent, so they characterize convexity. Hessian positive semi-definite characterize convexity. If we have strict inequalities here, we characterize strict convexity, and if we have strict inequality here, it's sufficient for strict convexity but not necessary. This part here, it's easily seen by f of x equal to x to the 4. Then the Hessian is second derivative, and it's 12x squared, and this is equal 0 for x equals 0. So this is not positive definite at every point. There's points where it's 0, but it's still strictly convex. Okay, so we dealt with this already. Okay, let's prove the rest of the equivalence. Okay, let's first start 1 implies 3. So 1 implies 3. What we do is we take the convexity inequality, so lambda x plus 1 minus lambda y plugged into f is smaller or equal to lambda f of x plus 1 minus lambda f of y. And then we rearrange 2, so we take actually lambda positive but smaller than 1. And then what we do is we subtract f of x on both sides. And then do we? No, we do something different. Let me check. So I said we rearranged 2, and then probably I rearranged wrongly, but somehow in this direction it should work. So we rearrange to f of first this here we write this as x plus lambda y minus x. That's actually the same thing here, the argument, just written differently. Minus f of x divided by lambda smaller equal to f of y minus f of x. So I guess this is right. Probably but I think it's still true. I think it's 2. Yeah, I guess that's 2. So now the thing is, if you have this, what happens if we now let lambda go to 0? So this, we can do this for our lambda positive, but if we let lambda go to 0, then this here is actually the directional derivative of x into the direction of that. So because f is differentiable, the directional derivative of f is totally described by the gradient. So this actually converges to the gradient of f at x in times y minus x. And then that's already it. So that's already it. Okay. Okay, that was one was very quick. 1 implies 3. 3 implies 2 is even quicker, probably. We take this inequality, that one here, and write it 2 times with the x roles of x and y swapped. So we have f of y is larger equal f of x plus gradient of f of x minus y minus x, and f of x is also larger than f of y plus gradient of f at y at x minus y. So kind of we linearize 2 times, once here and once there, and then if we just add them, we get yeah, maybe I write down everything. If we add them, we add them and go here, then we get f of y plus f of x is largely equal to f of x plus f of y plus yeah, how do we do it? If we add these 2 times, we see we could add them and we could use linearity, but this is one swapped, so we have to switch the sign in one of these. Probably we switch it over here. Then we have this positive gradient f of y minus gradient f of x, and then we have x minus y. So the thing is, these two things cancel out because they appear on both sides, and we have, this is already what we want on the wrong side of the inequality, but actually this one is not in the same order. We have y here and x there and y there, so this is actually what we want. So 0 is larger than this. We pull out a minus here, maybe by swapping these two terms, and then we bring it to the left hand side, and then we're done. Okay, and how do we get from 2 back to 1? So we needed to kind of produce a difference quotient here and pass the limit to get the derivative. Now you have to get rid of the derivative. So this characterization 2 uses the derivative already, and you want to go to a characterization which does not use the derivative. So we have to kind of integrate it out somehow. And that's what we do. We consider the function h of lambda, which is just f of x plus lambda y minus x. And then what is its derivative? Yeah, this is exactly the directional derivative here. This is exactly gradient of f at that point here, x plus lambda x minus y times no, this was y minus x, sorry. And here it would also be y minus x. This is y minus x. This is y minus x. Okay, and now we apply the fundamental theorem of calculus to this function here. So we try to integrate that out. So what we want to do is we integrate h prime of y over y. Sorry, that was a lambda. Oh boy, that was a lambda, and these are our lambdas. Lambda, lambda, lambda from 0 to 1. Because what do we get? Working to the left here, we get h of 1 minus h of 0. Right? That's just the fundamental theorem. So it's FTC, I think this is abbreviation in English, fundamental theorem of calculus. And then we have a look, what is f of 1? F of 1 is, h of 1 is actually f of y. And I see in the handout I did it differently. In the handout, I swapped the roles of x and y, but anyway, this should work like this too. And h of 0 is f of x. Okay, that's one thing. But now we just plug in our definition of h prime here, and we see this is the integral from 0 to 1 of okay, this is now gradient f of x plus lambda y minus x times y minus x d lambda. I see. Okay, what we do, I think we prove something else, unfortunately. Okay, anyways. I finished the argument here, but I guess we're going to prove 2 implies 3 here. So equivalence of 2 and 3, sorry. But anyway, let's finish this because it's, the argument is nice, and then we prove something more. But I think I have to think about the missing implication. So this is 2 implies 3, if I'm not mistaken. So what we do is we subtract, so we copy that here. And what we're going to subtract is gradient f of y times y minus x on both sides. So this is here and here. This does not depend on lambda, and the integral goes from 0 to 1, so we can just put it inside the integral here. And if you just put it inside the integral, we see that this inner product here has the same thing on the right hand side, and so we can have something like f of x plus lambda y minus x minus gradient f of y times x minus y d lambda. So we had subtracted this here on the right hand side and pulled it inside the integral. Okay, now the thing is that this here is actually larger or equal to 0 by monotonicity. You have 2 says monotonicity of the gradient, and if you see the difference of these two things, x plus lambda y minus x minus y, this is equal to, how do you say, this is 1 minus lambda times x minus y, actually. Is it the wrong way around? Hey, sheesh, I screwed that up here. Because this is now the wrong way around here, but it seems to be true like this. Oh boy, I screwed it up. Okay, let me check. So this would be then, this would say that this is non-positive, then this would go like that, and that's the wrong way around. Okay. Okay. So what we do, we just make a question mark here and say to be corrected, and I correct it later on. I probably don't correct it here on the fly. Sorry. But that's not that bad because today I have a strict deadline in the end, so I can go over time. I have to recheck this argument here and correct it. It goes like this, but somehow I got confused by the order of arguments. This is what I said last time. I always take great care of the order of arguments, so you don't get confused. So I correct that, and also I add the missing implication from 2 back to 1. Sorry. Okay, this is to be corrected, sorry. But for the twice differentiability, that is hopefully simpler, but maybe I recheck that too, and I give you the full argument at a later point. So I will probably just make a video of the proof of that, sorry. Okay. But anyway, the characterizations are true as given, that is for sure. So the characterizations which you read there are true, so we can use them to write down a few examples. So for example, one class of convex functions look like this. So we take a matrix A, which is D times D, and a vector A, just a small a and capital A, which is a D vector, and a scalar B. And this function is convex if A is positive, semi-definite, and strictly so if A is strictly it's positively finite. And well, why is that? One thing is that the gradient of f of x is just A. That's just how it is, and the Hessian, pardon, and the gradient is, if I'm not mistaken, it should just be ax plus small a. Okay. Good. You could maybe would also be interested to analyze so strict convexity if it's actually positively finite. How about strong convexity? Is it even strongly convex? And yes, it is. So you can characterize strong convexity by properties of this matrix A alone. But the question is now, what's the constant of strong convexity? You may want to think about that. Okay, that's one example. Another example, which is also of practical relevance, is the so-called log sum x function. So log sum x, I write it actually as log sum x of a vector x in Rd. And this is basically doing what it says. It takes log of sum of x of the xi. And it sums from 1 to d. That's the log sum x function. And it's interesting because it's close to the maximum of the xi. But it's not exactly the maximum. So you can rescale it that it comes closer and closer to the maximum. So it's a kind of a smooth approximation to the maximum. So it's a function from Rd to R. And this is convex, and we're going to show this by using the characterization by derivatives. Okay, let's calculate the gradient and the Hessian of that guy here. So we call this here h of x, and using this is then log of h. We can calculate the partial derivatives of the log sum x of x. So and then it's the log of something. So what we have here is the partial derivative of h divided by h, by logarithmic differentiation. Okay, what is the partial derivative of h? H is this. It's just x of x1 plus x of x2. We take the partial derivative with respect to the ith variable, so we just get x of xi divided by h of x. So that's simple. But what about the mixed derivatives if we just take a second derivative? So what about the Hessian? Yeah, well, we should take a second derivative of this guy, and now we have two cases. Either the I is equal to j, then we have a quotient of two things which depend on xi. But if j is not equal to I, we only this denominator here depends on the j's variable. So we have two cases here. The case where I is equal to j, and the case where I is not equal to j. In the case where I is not equal to j, it's actually pretty simple. We get minus x of xi, plus xj divided by h of x squared. This is what you get. So this is kind of the new partial derivative of h. It comes up here. Okay. And up here you take the full quotient rule and get x of xi times h of x minus x of 2xi divided by h of x squared. This here is the same term as here. If y is equals j, this is 2 times xi. Okay, so these are the entries of the Hessian, and with this we calculate now positive definiteness of the Hessian. Yeah, well, so these are the entries of a D by D matrix, and if you know, so what do you do about positive definiteness? Well, calculate the eigenvalues. No, don't try to do that. Calculating D eigenvalues, I have no idea if this is even possible. But what is possible is to check the definition of positive definiteness in the way like that we just here put here the Hessian into the inner product. So we multiply from the left and from the right. So log sum x of x times the vector z times the vector z. And we analyze this expression here. Okay, and then it's not totally difficult to calculate that. First, we can just get one of these factor 1 over h of x squared out, and this is nice because it's non-negative no matter what x. And if we then write out what's happened with the inner product with multiplying by z and by z here, it's basically just multiplying by zi squared or zi times zj here. And if we do that carefully enough, we get h of x from here times the sum I of 1 to d x of xi times zi squared minus a double sum over all I and j from 1 to d x I plus xj times zi zj. And so this term here comes from this expression, and these two expressions give this one here. Notice that I did not exclude a equals j in that sum. The terms I equals j, we have x 2xi here, and these come from here. Okay, so then what we do is we use that we know what this h of x is. H of x is just the sum of x of xj, for example, I from 1 to d. And so we have a double sum here too. It doesn't look like it, but it's actually a double sum. So this is a double sum, that's also a double sum. So we can rearrange or rewrite this as the double sum here. I and j go from 1 to d. And we have a x of xi times x of xj. So we have an x of xi plus xj times zi squared minus the sum over I and j from 1 to d, the same thing, x of xi plus xj times zi times zj. So now we make a trick and write this guy here in two ways. So because we can just, if you have zi squared here, or zj, it doesn't matter for the full sum. So if you would replace the I by j here, the sum would stay exactly the same. So we can write this term as 1/2 the one we had, zi squared, plus 1/2 the same sum times zj squared. So that's one trick here, which we can do. And what we then see is, if we get everything under one big sum here, which we can do because the summation is always going over the same thing, so it's ij from 1 to d, then we can pull out the exp, xi plus xj, and have 1/2 zi squared plus 1/2 zj squared minus zi times zj. Okay, and this now is the perfect square. That is 1/2 zi minus zj squared. Okay, so this is always the thing, if you want to show that something is positive semi-definite, it has to be kind of a sum of squares in zi and zj. Okay, and now everything is non-negative. This here is non-negative, that is always non-negative, this here is non-negative, everything is non-negative, and this is what we wanted to show. So this shows that the log sum x function is actually convex. Okay, so I think we make a short break before we come to the rest of the characterizations of convex functions, because I have to be firm in the end at 11:15. Okay, short break, 2 minutes, a few more dad jokes and relaxing music. So see you in 2 minutes. Okay, here we are back. Okay. Okay. So, yeah, convexity characterized by derivatives. So Hessian is positive semi-definite, or gradient is monotone, which is kind of I can't picture that in my head what that means, but what I can picture is the function is above its linearization. That is a very, very handy and important characterization of convexity. And the monotonicity will also we also make use of monotonicity later on, although it's not that kind of visual property, at least for me. If someone has a good visualization of monotone maps from R2 to R2, I would like to see that. So what about characterization by epigraphs or level sets? So we did that for lower semi-continuity. We could say a function is lower semi-continuous if and only if the epigraph is closed or all of its level sets are closed. So, so how about convexity? So the level sets alone are not enough to characterize convexity. That is pretty clear if you just consider a function like that. If you consider a function like this, all the level sets are intervals, no matter where you put the level. But the function is not convex. So this line here lies, this secant lies below the graph. So convexity of the level sets are just not enough to characterize convexity of the function. There's actually a name for functions for which all level sets are convex. These are sometimes called quasi-convex. But actually this property is not so nice. So quasi-convex functions also have the property that local minima are global as far as I see. Yeah, but other things are missing. So for example, the property that the function is above the epigraph, it's not there. Above the tangent, it's not anymore there. Okay, but for the epigraph, everything is true. So the proposition goes like, as you would like to have it, f of from Rd to R is CVX if and only if the epigraph is convex. So that is as simple as it can be, and the proof is more or less straightforward. So f equal to plus infinity, we don't have to do anything about it. Then the epigraph is empty, everything is fine. So now consider the case that the domain of f is not empty, so we have at least finite points. The function is proper. So to go from here to there, f should be CVX, and we should have 2 points in the epigraph. Okay, meaning that f of x is small or equal to a, and f of y is small or equal to b. And then if we take a lambda between 0 and 1, we have that by convexity f of lambda x plus 1 minus lambda y small or equal to lambda f of x plus 1 minus lambda f of y, and this is small or equal to lambda times a plus 1 minus lambda times b. Okay, but so now we have another pair. The function at this point is smaller than that value, which means that this pair here is in the epigraph. So this just means that the pair function value and point, or value and point, is in the epigraph. So this means the pair lambda x plus 1 minus lambda y and lambda a plus 1 minus lambda b, which is now in Rd times R, also in the epigraph of f. And if you have a closer look, this is actually the convex combination lambda times the vector x and a plus 1 minus lambda the vector y and b. So now we have it. So we have these 2 points in the epigraph, and then the convex combination is in the epigraph as well, and that was that. Okay. Yeah, and sometimes I write these tuples as in this way or in that way. It depends on, I don't know, which I like better. Okay, to go back, it's basically similar. So let the epigraph of f be convex and take 2 points in the domain of f where we don't allow a point minus infinity. Actually, we've seen that minus infinity is it's a very rare thing to happen for convex or for lower semi-continuous functions. Anyway, so what we know is that both the points f of x and f of x and the point y f of y, they are both in the epigraph. And thus we can take the convex combination of this, which is again in the epigraph. So we just write down the convex combination. It's lambda times, and probably I should write it like this here again, plus 1 minus lambda y f of y, which is just as before, lambda x plus 1 minus lambda y, lambda f of x plus 1 minus lambda f of y, and this is again in the epigraph of f. And meaning being in the epigraph means that f of this is smaller than that. So this means f of the former argument here is smaller equal the lower value. And there was that. Except for if one point assumes the value minus infinity. I just write down how it goes in principle. Then we use x and minus n instead of x and f of x, and let n go to minus infinity. This kind of works basically the same. Okay, but anyway. Actually, convex function would assume the value minus infinity can never assume anything else than minus infinity or plus infinity, or only at very special points. But okay, this situation is, I never encountered this situation in my life, so I don't think about it too much. Okay, so but now if convex functions are characterized by convexity of the epigraph, we can apply separation. That's a good thing. So picture goes like this. If this is our convex function, this is the epigraph, we can always find lower, for every point below we can find a separating hyperplane, and we know that hyperplanes correspond to affine functions in some way. So now we can find affine functions below. Okay. Even without differentiability. We talked about a picture like this in the case of differentiability. Convex functions need not to be differentiable. So, but anyway, we still have kind of affine functions below. So that's the content of the next proposition. So if f of Rd to R is convex and proper, meaning that there's at least one finite value, then there exists P in Rd and an offset, or it's called alpha in R, such that the convex function is bounded from below by an affine function, like this. So, okay, coming back to the to the first thing about minimizers, the standard question. So these are the bad things when it comes. One of the bad things when it comes to minimizers, but it can go faster to minus infinity than that. So because for each convex function there's the affine function which bounds it from below. So this cannot go faster to minus infinity than this affine linear function. That will be handy at some points if you're gonna, in some applications when you want to prove something about like existence of minimizers. The different first bound, lower bound convex functions always by an affine function. So then you have the escape to minus infinity cannot be faster than linear. Okay. Okay, so how does one prove it? Of course by separation. Oh, and note that we did not even assume any regularity here, so no lower semi-continuity is assumed. So but we know that for each function we have this closure of the function, which is basically the lower semi-continuous envelope, more or less, and it's always below the function. So if we have a non-lower semi-continuous function, we can kind of close it to a lower semi-continuous function. So only need to know the case, only assume f is closed, hence has closed epigraph. Okay, and then if x is now not in the domain of f, we always have this inequality. Where is it gone? We always have the inequality here. If f is not in the domain, that's always fulfilled because this is plus infinity. always holds. Okay, now we fix some x0 in the domain of f, and the beta such that f of x is x0 is actually larger than beta, which means that the tuple x0 and beta is not in the epigraph of f. So we have our convex function here, like this. We have fixed one x0 and the value beta, so that this is x0 beta. The function value of f and x should be above, larger than beta. So this is the point here, and this is not in the epigraph. Okay, but this epigraph is now assumed to be closed, so by our previous consideration up here, epf is closed and convex, and hence we can separate it from the point. Can be separated from the point, from the set which only contains the point x0 and beta, and this means there exists a p which I call p bar and something which I call minus b for some strange reason which become clear later on, a vector in Rd plus 1 which is not 0, such that so we can even strictly separate, no? Because we know if this closed epigraph and this closed and compact point, so we can strictly separate these two sets. So there's also this exists and also an epsilon, a positive epsilon, such that for all x in the domain of f it holds that the inner product of these vectors which points in the epigraph, which then boils down to p bar times x minus b f of x. So this is actually the inner product of p minus b with x f of x. Looks like this, and this is always smaller equal than the same thing when we do it to this point here, so to all points in the other convex set. So this is here this is in the epigraph of f. And here we have p bar times x0 minus b times beta, beta times b, even minus an epsilon here. So we can strictly separate, so this gives us the leverage of 1 epsilon here. Okay, this is not strictly a separating hyperplane already, because, well, we don't know what happens to the b. So if the b is 0, then this would be a vertical hyperplane. So we kind of need to exclude the case that b is 0. B is 0. But that's not that difficult, so we can plug in x is equal x0. Then these two terms will be the same and vanish, and the inequality can be rearranged to b times f of x0 minus beta is larger or equal to epsilon, which is positive. So, but this is positive by assumption. So b has to be positive by assumption. Consequently, b has to be positive. Especially it's not 0, so when we can consider, we can redefine or define now p as p bar divided by b, and this gives, so we take this inequality here again. Actually, I don't need this. Gives then, if you have a look what happens here, so if we divide by b, we can just divide this full inequality here by b, and b is non-negative, it's even positive, so we can divide without flipping the sign here, and we end up with, after a little bit of rearrangement, f of x is larger or equal to p of x, p times x minus p times x0 plus beta. We even omit the epsilon, we don't need it anymore, and so we just set this thing here to alpha, and we are done. And the only thing is, so two ideas in the proof: separate the closed epigraph from the compact point, and then ensure that this hyperplane is not vertical. Okay, good. that was that. Okay, so and now it's a simple exercise, and actually I think it is an exercise if I'm not mistaken. So if you have a convex function which is not necessarily lower semi-continuous, then you should show that if you take all minorizing affine functions, all of them, and take the supremum, the pointwise supremum over all minorizing affine functions, then you get back the closure of f. So it's not really that much to do. So if f, sorry, I forgot here this. Is it a typo in the lecture notes also? So this should be value infinity was allowed here. Yeah, I just forgot to put it here. The same is here the case. So if we have an extended convex function, then we have that the closure of f at some point x0, pointwise actually, is exactly the same as supremum of the value of some affine functions, but we have that for all x's that f of x is larger or equal to this affine function. So this means that if you take the supremum over all affine functions below, you will get exactly the value of the closure at that point. Okay, and so then we're almost done, which is nice because so then I have no hurries don't have to hurry too much to get to the next meeting. So what is the last thing? This is a very simple proposition, and it's similar to what we already did for convex, for lower semi-continuous functions. Lower semi-continuity is preserved under a lot of operations, and the same is true for convexity. It's also preserved under a few operations. And so, and it's all straightforward to prove from definition. Yeah. So if f1 plus f2 is convex, if f1 and f2 are convex. So sum of convex functions is convex. Just use the definition. So we could have stated this proposition earlier, but anyways. Second is that alpha of f, alpha times f is CVX if f is convex and alpha is non-negative. So it does not work with a negative alpha, of course, then you flip convexity to concavity. So once again, Tooth says that convex functions form a cone. Okay. Precomposition with a linear map gives convex functions. So this is convex if f is convex and a linear. Okay. So precomposition by a linear map, that is nice. Postcomposition by a linear map, it's also nice, but you need non-negativity here. What about postcomposition of a convex function phi times f? That's CVX if f is convex if f is convex, but what about phi? Phi, now we need to take a little bit of care because f may assume the value plus or minus infinity, so we have to allow phi to also map the values plus and minus infinity to something. So what is now the conditions on phi? And not surprising maybe is that you need convexity of phi, but that's not enough. So convex composition is not always convex because we need something, and we need increasing and increasing. But that's not enough. Convex and increasing. Yeah, and then now I think maybe one of these edge cases escaped in this here, but anyway, of course this is helpful. F of infinity is infinity and f of minus infinity. Phi of infinity is infinity and phi of minus infinity is also minus infinity, and I'm not totally sure anymore in the edge cases, but this minus infinity always annoys me. Okay, but for at least for finite values, that's fine, and you should just not map plus infinity to something else into plus infinity, and minus infinity should not occur at all when it comes to me. Okay, and the last thing is that the supremum of fi over an arbitrary index set is convex if all fi convex. Okay, yeah, that's now it, and it's very simple to prove, to just plug in the definition. In most cases, yeah, I mean, basically it works in all cases. Especially here, if you work out the proof, you see that without increasing, you can't get this one inequality happen. Can make it happen, yeah. So one could try to prove a few things also via the epigraph. So then you have to figure out what happens to the epigraph under this condition. So this is simple, and the epigraph just gets scaled in some way. So this is nice. This is not so clear what happens with the epigraph. So I would rather prove this by the algebraic inequality. Here it's not that bad because it's intersection of the epigraph. So if you have one convex function and another convex function, then the supremum is this, and you just intersect the epigraph. So that works simple, and so intersection of closed convex sets is closed convex. That's then fine. Intersection of convex is convex. For this is not clear at all to me what this does to the epigraph. It does not add the epigraph, that's for sure. It may do different things, and I'm not really sure. The addition of the epigraphs, by the way, is also an interesting thing, and we'll come to that. So what happens if you add the epigraphs in the sense of Minkowski sum? That's an interesting operation, and we will come to that. It's called EP addition or infinite convolution. I think next week. Okay, and now that's a very simple example. So we had the log sum x function, of which I said it approximates the maximum and of d numbers, and of course f of x, which is then defined as the max of x1 to xd. It's exactly of this type, and inside they are all linear functions. Linear function is convex. The supremum of convex function is convex. So this is the convex functions by number 5. Okay, yeah, it's a bit early because I screwed up this proof, but I'm gonna fix it, and I'm gonna upload a video here where I fixed it. Probably I will not do it live, but do it offline, and just let you know when it's there. Okay, sorry again for screwing up. Actually, these implications they are not really deep, but they are powerful, and for some reason I did not prepare them carefully here. Sorry for this. I'm going to fix it. Okay, that's it for today. Next lecture is tomorrow at, I always forget, I think it's 11:30. Yeah, tomorrow at 11:30, and then it will be about continuity of convex functions. That's another miracle. So today we saw that we have lots of characterizations, even these characterizations from the outside via suprema of affine functions. And then one more thing which kind of really surprises me always is that convexity implies a certain notion of continuity, which doesn't make sense if you think about it first, because convexity is purely algebraic. So you just write down the convexity inequality f of lambda x plus 1 minus lambda y smaller equal 2, and the x and y should just come from some real vector space. You don't need anything of this real vector space. No metric, no norm, no topology, no whatsoever. But still there's a theorem like convex functions have a certain kind of continuity. And where does this come from? Where does this topology come from? Okay, we will see it because it's not true in this sense. It's kind of only true in a little limited sense, and then you will probably see where the topology comes from. Okay, that's it for today, and see you tomorrow.